Hi everyone. This is a quick tutorial, probably about half an hour or so, on the fundamental forces and on quark structure. So where we left off last time, and if you are not sure about this, obviously, if you haven't seen the online lesson yet, then you need to make sure that you've gone on my YouTube channel to watch that online lesson about atomic structure. We're going to move on now. We're going to talk about quarks and fundamental forces. So we're going to start off with a quick puzzle. This is a puzzle I started off with in my original lesson, which was before the lockdown. So it was in the classroom, where I asked the question: if you've got, bear with me, if you've got two protons and two neutrons, in theory, those two protons should fly apart. They should repel, which means that you could never have your helium nucleus. You could never have it. It wouldn't exist. The only the only game in town, so to speak, would be hydrogen, because any other nucleus would just fly apart. So something else must be holding them together. So with our nuclear model and our basic understanding of physics, we can't possibly explain exactly how and why we have different elements and different nuclei. So it can't explain everything. So we have to start to think what's going on here. Well, there must be, if there's a repulsive force, there must also be an equal and opposite force that's trying to attract them. But what force is it? Well, it's a force. It's very difficult to remove nucleons from a nucleus. It does require a lot of force. So it's a strong force. And that strong force is a very simple one. Well, it's not actually, because there's something very, very weird. There is a strong force that's doing two jobs. Here, it's holding the nucleus together. But if we think about it, what's stopping the two protons combining to form an extra big proton? Okay, we don't get those extra big protons. Why not? Well, there must be something that if you try and push the two nucleons together, then they will try and repel. So what's actually happening is that if you have the two nucleons like that, if you've got your two protons, if you look at the force versus their distance apart, we get a particular place where there is no force. Okay, that's like an equilibrium position. Okay, it'd be about there actually. So what actually happens is that the nuclear force is obviously going to be repulsive at first. If you try and push the two protons together, they'll try and push apart again. Then they become attractive. Oops, something like that, dropping off to zero at a very, very short range. So what happens is that there is a force that doesn't really follow the unified field forces that we looked at before. Because when you looked at the gravitational force, we know that the attractive force, so it'd be like that, would be something like that. It'd be forces proportional to 1 over r squared. Okay. If we look at the electrostatic force, versus the distance between two particles, it would be a repulsive force if they're both positive charges. But again, force proportional to 1 over r squared. It doesn't follow, the strong force doesn't really follow that rule. Okay. So we ended up with an extra force. Well, as it turns out, to jump forward a little bit, because this is a revision lesson really, it's just that one of the things that came up in some of my assessments was a need to really sort of just brush over the brush up on the fundamental forces and on quark structure. So there are actually four forces. We start off with the one that's the weakest, gravity. Okay, if we think about it, we know that if you've got two masses, they will be attracted to each other. we know that that force is absolutely tiny unless one of the masses here, or one or both of the masses here, is very, very big. Then we come into some other forces. We have electromagnetic. Now, electromagnetic forces said if you've got two positive charges, they will repel. Well, the arrow's the right way around and we'll be happy. They'll repel. Okay, so we have those two. You knew about those two. Now we have this strong force. Now the weird thing about the strong force, as we said before, the force drops off very, very rapidly when very rapidly when you change the distance. Now think about it. We don't really see a strong force outside of the sort of scale of the the nucleus. So we know that the range of the strong force is more or less about 10 to the minus 15 meters or so. It's got a very, very short range, which is pretty useful because it is a very strong force with respect to all other sort of factors. So it means that if we saw it outside of the nucleus, it would be pretty much the dominant force of the universe. So it wouldn't make much sense for it to have a range beyond the size, beyond the nucleus. And then we have an extra force that I've not really touched on, called the weak force, and we'll come on to this when we go back to decays in a moment. The weak force has an even shorter range. It actually only happens inside nucleons at what we call the quark level. So we need to understand what quarks are. The idea is meant to be that when you have quarks, when we start sort of go beyond our conventional nuclear physics, we start to go into the nucleons. Now, the previous lesson from last week, I talked about how we know about quarks, the idea about particle scatter, about electron scattering. We found out that electrons were being repelled by protons, which wouldn't make sense. Opposite charges should attract, but here we had an electron coming that way and rebounding, which shouldn't happen. So there must be some some negative charge inside a proton. Well, as it turns out, there are actually three charges. So three charges, if I take three charges like that, what actually happens is that they're all sort of bound together. When they're bound together, they're sort of stuck. They're attracted by actually the strong nuclear force with particles, with exchange particles called gluons. And because they came in three, there's a literary reference that talks about something coming in three as being quarks. So they came up with the idea, the scientists came up with an idea of calling them quarks or quarks. Now, as far as you're concerned, there are actually only three types of quark. However, three types of quark. However, there are actually six, but you don't need to know about the other three. So basically, they found out that there were three types. There was up, down, and because initially we only thought they were only up and down quarks, when the third type of quark came along, we thought it was strange, so they called it. So it was referred to as a strange quark. I suspect because it was strange. It maybe sort of messed about with our theories a little bit. Now, what you really need to know there is what's called the relative charge. We tend to ignore the little r. I'm going to start ignoring that little r, by the way. So the up quark had a charge of plus 2/3. The down quark had a charge of minus 1/3, and the strange quark had a charge of minus 1/3 as well, but it had a much bigger mass than the down quark. So initially, I suppose if you only looked at the charge, you would have thought a strange quark was the same thing as a down quark, but it has a much larger mass, which is strange. Now, this can actually be used then to predict to predict the quark composition of neutrons and protons. So a neutron and a proton, there we are, we know that its relative charge, as I said, I'm going to stop using the little r, of a neutron is 0, and the relative charge of a proton is 1. So how do we get 1 out of just these two? So if you imagine that there are 3, you've got to have, well, to get neutral, if you have 3, if you combine 3 quarks, you could only have, if you have the up quark, that would be a charge of plus 2/3. So you'd need to take away 2/3. Well, down quarks both have a charge of minus 1/3. So it's plus 2/3 relative charge, minus 1/3, minus 1/3 equals 0. And similarly for the proton, if we think about the proton's got a charge of plus 1. So if the proton's got a charge of plus 1, you're going to need an up quark to make plus 2/3. You add another up quark and you end up with plus 4/3 or 1 1/3. So you need to take away 1/3. So the way you do that is you add a down quark. So you've got up, up, down. So you have plus 2/3, plus 2/3, minus 1/3, it's going to equal 1. Okay? And that's the basic idea behind quark structure. In order to go beyond that, we need to start thinking about interactions. And this is also quite important. So if we think about interactions, we have to start looking at what we call standard model numbers. So if you have any interaction, an interaction could be something like alpha decay, beta decay. It can be anything that happens inside the nucleus. The ones that you will come across are usually things like beta minus decay and beta plus decay, but there may be some others. So an interaction is basically, they follow certain rules. They're conservation rules. As I said in many times, as I've said many times, physics follows patterns. It's one of the things I love about physics is it follows basic good patterns. So our conservation rules are that if you have the charge is always going to be the same, just like it was with the nuclear interactions. But we've also got to think about three other particular things. We have a thing called the baryon number and the lepton number and strangeness. The only time when strangeness is not conserved is in weak interactions. Remember, when I say weak, I'm referring to interactions that occur due to the weak nuclear force. So we've got to find, remember what these are. Well, in order to understand what those were, we've got to go back to our sort of standard model. The way to look at it, first of all, is to understand that in our universe we have matter. That's any kind of particle. Now, with matter, we have two particular groups, hadrons and leptons. We also have bosons. Now, bosons are the particles responsible for all the forces that I've mentioned earlier in theory. We've detected, obviously, that there are bosons that we've detected. There are bosons that have also been predicted. There are bosons where we think we've detected them. So, for example, the Higgs boson. And the bosons are responsible for those four fundamental forces. Instead of having a field at the sort of the very, very tiny level, we can start to look at forces more in terms of exchanging particles. Now, when we split the matter into the three types, the ones you need to know about are leptons, and these are electrons and neutrinos, and of course also the antiparticles, the positrons and antineutrinos. Hadrons split into two further subgroups, mesons and baryons. So how do we spot them? Well, leptons are fundamental, okay? They are not made of anything. They're not made of any particular other particles as far as we know. Hadrons are not fundamental because they're made of quarks. Okay? So they then split into two ways you can make particles out of quarks. The first one is a meson, and that's usually a quark and an antiquark pair, like that. So remember, the bar at the top usually means antimatter. So they would say, for example, for a pi plus particle, you might have, say, an up quark and an anti-down quark. Okay. So if you think about it, the charge, if a plus, the charge is going to end up being +1. So the charge here is +2/3. Now, the antiparticle, remember, anti means opposite. So where we go back to our quarks, the down quark has a charge of -1/3. So the anti-down quark, or the down antiquark, has got a charge of +1/3. And so on. So that's what a meson is. It's a pair joined together of a quark and an antiquark. Baryons are always 3 quarks. So for example, a proton is an up, down. Is 2 up quarks and a down quark. Okay. So here, when we have a baryon, if you've got a proton, so in other words, protons and neutrons form these baryon particles. Now, if you think about it, if you have a proton and a proton is a baryon, the number of baryons you have is 1. So for protons and neutrons, both have a baryon number of 1. However, leptons are not baryons, so the baryon number is equal to 0. But as they are leptons, their lepton number would be equal to 1. So here, these are not leptons. So the lepton number is equal to 0. Now, if you've got, so that must mean each quark, because if you've got 1 and you've got 3 quarks, each quark must have a baryon number of 1/3. If you have an antimatter equivalent to a quark, the antiquark, it's going to have opposite properties. So it's going to have a baryon number of -1/3. Simple as that. So if you've got anti-up, anti-up, anti-down, that is an antiproton. It's an antimatter equivalent to a proton. So if that's the case, the baryon number is -1/3, -1/3, -1/3 equals -1. It's an anti-baryon, if you like. And that then starts to take us through the basic sort of standard model. Now I'm going to go a little bit beyond the exam here, because I think that I really would like to sort of talk you through something closer to the complete picture. Now, 10, 15 years ago, this was the complete picture. Now it's a little bit different. But basically, we have a thing called the standard model. And so what we have on one side are quarks. And we also have leptons. And we have our bosons. This is really just because you may hear of the names of these in passing in the future. So it's worth knowing a little bit about them. So, excuse me. So what we've got here are quarks. And the quarks, basically, we already know we've got up quark and a down quark. So the up quark has a charge, there like that. The up quarks have a charge of plus 2/3, and down quarks have a relative charge of minus 1/3. This is 1/3 of the elementary charge. In with that, we also have the strange quark, which also has the same charge, same relative charge as the down quark. And there is actually another one called charm. And then also we have top and bottom quarks, which follow that same rule. Remember, you won't really come across these for the Cambridge A-level course. Okay, we know the baryon number of each one is plus 1/3. Okay, it follows exactly the same rules. With leptons, we know that we have electrons and we have neutrinos. Now, we also have a basic set of rules. Here, the relative charge of the electron is -1, and the relative charge of the neutrino is 0. Now, as we've got 6 fundamental particles here, it would be symmetrical to assume that we have 6 fundamental particles here. So we've got the muon and the mu neutrino and the tauon and also the tau neutrino. Okay, these are just Greek letters, mu and tau. Again, very unlikely that you'd ever come across this in A-level physics for the Cambridge syllabus. So you don't have to worry too much about that. But it's just to show you that there is a symmetry. Now, again, with bosons, we've got the graviton, which is the particle responsible for gravity. It's theoretical. No one's really, I don't think anyone's actually detected graviton itself. We've detected gravity waves, but not a graviton. We have, for the strong force, we have a particle, well, as it sticks the particles together very, very strongly and has a short range, we call them gluons. Okay, that's the strong force. And then for the weak force, we've got W+, W-, and Z0 particles. Okay, again, you're not like to come across in any of this. And then we start to have photons and possibly, well, getting fairly certain there is something there, the Higgs boson. Okay, so that is more or less the structure of our universe. But for every one of these, there is also an antimatter equivalent. So the antimatter equivalent to quarks, or to quarks, would be, well, anti-up, anti-down, anti-charm, anti-strange, anti-top, anti-bottom. And remember, these we don't have to worry too much about, but these would have a relative charge. Instead of being plus 2/3, it's minus 2/3. And a baryon number of minus 1/3, because it's an opposite property. Same likely here, as our charge is minus 1/3, the opposite is plus 2/3, plus 1/3, and the baryon number again is minus 1/3. The same happens here. But remember, the positron is the exception to the rule here, simply because we discovered the positron, scientists had discovered the positron before they knew about antimatter. So the equivalent to an electron is actually a positron. You could put a minus sign on these if you wish to. It would be a positron, the anti-neutrino. Then you have the mu plus and the anti-mu neutrino, the tau plus and the anti-tau neutrino. Okay, the charge is exactly the opposite, so it's now +1. So here it's just still 0 because the other side of 0 to 0 is 0. And we can think about the lepton number. These have all got a lepton number of +1. Okay. So these have a lepton number of -1. Okay. And that is exactly how the antimatter works. The point is that the antiparticles have the exact opposite properties. They're the same mass, everything else is the same. They're the same as, so the positrons are the same as electrons, but they have the exact and opposite properties, such as charge and lepton number. So where does that all fall in? Where does it all fall in? When we go back to our conservation rules, when we've got a conservation rules, we knew that these things are actually always conserved. So if we think about our interactions, you might have, let's say, beta minus decay or beta minus emission. We now know what beta particles are. We know how they're emitted, but we don't really know what's actually really going on. We worked out what's going on inside the nucleus, but do we know what's actually happening at a deeper level? So remember, a beta plus decay, an example might be carbon 14 decaying to nitrogen 14 plus the beta minus plus the anti-neutrino. So what's actually going on there? Well, we know that with beta minus decay, a neutron is decaying to a proton plus an electron plus that anti-electron neutrino. And we could actually start to apply our conservation. Now, this is a weak interaction, and you'll see why in a moment. There's Q, B, and L. Relative charge, baryon number, and lepton number. And all we really have to do is look at what's happening before and after. Conservation means the same before and after. So the charge of a neutron is 0. A neutron is a baryon, so its baryon number is 1. It's not a lepton, so its lepton number is 0. So it must be the same as we move on. So if we've got a proton here, well, we know a proton has got a charge of +1. We know it's a baryon, so its baryon number is 1. It's not a lepton. So if we think about it now, we've got electrons. Now electrons have a charge of -1. We know that they're not baryons. They're in a different category. So their baryon number must be 0. And they have a lepton number of +1. So if we then look at the properties for the neutrino, the charge is 0. It's not a baryon, so its baryon number is 0. But now it's an anti-lepton because it's an antiparticle. So instead of being +1, lepton number is -1. And we just add them up. So it's actually, so that is a correct sort of decay. Now what's actually happening here is inside here, you've got your quarks changing flavor because you have an up, down, down. That's what makes a neutron. Two up quarks and a down quark make a proton. Now these are not made of quarks, so there's no quarks involved here at all. So what must be happening is that one of these down quarks becomes an up quark. So what's actually happening is the down quark, oops, get off the page. There we are. Down quark becomes an up quark. Now it does that, if we think about it, if that's got a charge of -1/3 and that's got a charge of +2/3, it's got to lose a negative charge. Okay. Similarly, if we look at things like beta plus decay, beta plus decay is a fairly simple thing. It's almost exactly the same. I'm going to try and I'm going to try and think of a more realistic version of a more realistic version of a beta plus decay. So let's imagine we've got nitrogen, okay, with 7 protons, and it's actually for beta plus decay. What makes it most likely to happen is, oh, go out of focus. There we are. What makes it most likely to happen is if you don't have enough neutrons. So let's say we only have 11 particles in total. What actually happens is it becomes a proton. It turns into a proton. So we know that's going to be 6, so that's going to be nitrogen. And the same number of particles, because we're not going to be emitting any further baryons. Plus, now remember this is going to be the positron, or beta plus. So it's a positron, and it's an electron neutrino that's also produced as well. And we can start to think about what's actually going on. Well, here what's happened is a proton has decayed to become a neutron plus the positron plus neutrino. So we can quibble it. So the charge on the proton is 1, baryon number is 1, lepton number is 0 because it's not a lepton. Afterwards, neutron has got a charge of 0. The baryon number, well, neutrons are baryons, so it's plus 1. And it's not a lepton, so it's 0. A positron has a charge of plus 1. Has a charge of plus 1. A positron is in the lepton family, so it's not a baryon. A positron is an anti-lepton. It's an anti-electron, so it's an anti-lepton. So electrons have got a lepton number of 1, so it's got to have a lepton number of -1. And the same goes with the neutrino. Here, the neutrino, the charge is 0. That's why it's a neutrino, it's neutral. Plus a baryon, well, it's not a baryon, so it's 0. Lepton number, well, this is a lepton, isn't it? It's a neutrino. It's not an anti-neutrino, it's a neutrino. So its lepton number is 1. So we add them up and we end up with 1, 1, 0, which is the same as we had before. So the charges are conserved. And remember, if we look inside the proton, what's actually happening? Well, we've got, that's going to be up, up, down, 2 up quarks and a down quark. A neutron is made of an up quark and 2 down quarks. And there are no quarks involved here again. So one of these up quarks has got to actually turn into a down quark. And remember, we call that a change of flavor. The type of quark, when we say types of quark, the word often used is flavor. So what's actually happening here is an up quark is changing into a down quark plus a positron plus a neutrino. And we can again do Q, B, L. Now we can't do S for strangeness. One, in this case, it's irrelevant anyway. But secondly, we've got quarks changing flavor. So if we had a baryon that had a strange quark in it, or a strange anti-quark in it, here, if it's a weak interaction, we've got like beta decay and beta plus and beta minus decay, then we'd expect that strange quark to possibly change flavor. So strangeness would not be conserved. So if we've got a charge of +1 here, so charge of the up quark is +2/3. It's 1/3 of a baryon, and it's not a lepton. That's what the up quark is. The down quark has got a relative charge of -1/3. The baryon number is still +1/3, and lepton number is 0. And then we can fill in exactly the same as we've done before. And we add them together. So -1/3 plus 1 equals +2/3. -1/3 plus 0, so +1/3 and plus 0 is +1/3. And 0 minus 1 plus 1 is 0. So the numbers are still conserved. Okay? Now, if you want, these are what we call weak interactions. Okay? So the idea is, in weak interactions, quarks can change flavor. Now, an interesting one is, when I was taught particle physics, I don't know if it's still the case, but when I was taught particle physics, I was told the correct spelling was the American spelling of flavor, because apparently the word was coined by an American physicist, I'm told. Don't know if that's true or not. Now, so what are the other interactions where we might get a strange particle? Well, let's imagine we've got a different kind of baryon. Let's imagine we've got a baryon made of an up quark, a down quark, and a strange quark. Now, if it was going to decay by weak interaction, it might decay into an up quark, a down quark, and an up quark. So it might decay into a proton. And what would happen if it decays into a proton? If that's going to have a charge, well, it's going to be plus 2/3, minus 1/3, minus another third. That would be 0. There a number, it's 3 quarks, so it's 1. Lepton number is 0. Its strangeness. Now, here's a weird thing. Everything else, if it's that kind of particle, its sort of quantum number is 1. Strangeness, it's minus 1. Okay. A strange quark has a strangeness of minus 1. I'd like to think that's probably down to particle physicists having quite a good sense of humour. So if we've got a Q here, we've got a charge of 0. We know we've got to end up with a charge of 0, but here we've got plus 2/3, minus 1/3 equals plus 1. It's 3 quarks, so it's a baryon. It's not a lepton, and there's no more strange quarks, strangeness. So the strangeness is 0. So we've got to think about what's left. Now we know if it's a weak interaction, it's going to be either going to be beta plus or beta minus, as far as we're concerned here. So if we think about it, it's starting off with a charge of 0. It's gaining a charge of 1, so it's got to lose a negative charge. So it would be an electron and an antineutrino, and we can verify this using our basic rules, okay? So the charge of an electron is minus 1, that's 0, so that would be 0. The baryon number of an electron is 0, as is the antineutrino. Lepton number is 1, and the charge, the lepton number of an antineutrino is minus 1. They add together to make 0. Have we got this right? No, I haven't. It's 1 plus 0 plus 0 makes 1. Okay, pay attention. So strangeness here, none of these particles are strange, so it's 0. So strangeness is not conserved, which was one of the reasons why it's a weak why we class it as a weak interaction, but everything else is. But now let's think about it another way. What can also happen is if you try to separate one of the quarks out from baryon, you actually can't get quarks on their own. So as you're pulling that quark away, you're pulling against a strong force. You're doing a lot of work. And that work is energy. And energy and matter are, to a certain extent, interchangeable. So what you could do is you get your up, down, and your strange quark, okay, to make your make your baryon, and you could try and pull out the strange quark. So you could make a proton. In order to do that, if you think about it, what you've got to do, we're magicking an up quark out of nowhere. When you want to do that, you've got to actually put some energy in, and you make an antiparticle that's identical, an anti-up quark. And the strange quark is also pulled out, okay? So what happens is you create a pair. You create a pair of quarks. Now, you don't need to, for Cambridge, you don't need to know about Feynman diagrams, but as we go up in time, imagine you've got the up down quark, the up quark, down quark, and the strange quark. Now we know that they stay together. But as you pull the strange quark away, what happens is you create a quark-anti-quark pair, or particle-antiparticle pair, which might be an up quark and an anti-up quark, okay? Because we know the opposite can happen with antimatter. When a particle interacts with its antiparticle equivalent, then they annihilate and they produce a pair of photons with an energy equal to the mass energy of the two, in this case, up quarks. So that's what's happened here. Now, when we do QBLS, charge, remember, is 0, 1, 0, 1 as before. And we know that afterwards it's going to be +1, +1, 0, 0. Now what we've got to do here is we've got to work out what this is. Well, the charge of an up quark is 2/3. So the charge of an up antiquark is going to be minus 2/3, and we know the charge of a strange quark is minus 1/3. So that's going to be -1. Baryon number, well, a baryon number of each quark is 1/3. So you've got 1/3 plus, well, it's an anti-quark, so it's got a baryon number of minus 1/3. So if that charge number is minus 1/3, sorry, baryon number is minus 1/3, you've got minus 1/3 plus 1/3 equals 0. The lepton number, well, it's a meson, isn't it? It's in that particle group. If I can find my notes I showed you before, it's in this weird sort of particle group called mesons. And here, the baryon number of a meson, because it's not a baryon, is 0. It's not a lepton, so its lepton number is 0. So we end up with plus 0 plus, now, strangeness. Here we have a strange quark, so its strangeness must be -1. So we add them together, and we got +1. Have we got this right? No, it's -1, isn't it? So it's +1 plus -1 makes 0, as we have before. Baryon number is +1 plus 1 plus 0 makes 0. So we've got 0 plus 0 makes 0, because there are no leptons involved. And if there are no leptons involved, it's another marker that it's a strong interaction. The strangeness is -1 at the beginning. The total is still -1 at the end. So it's possible, and it's actually what we call a strong interaction. And those are things that I think we needed to sort of brush up on. So what I'd like you to do now, bear with me, let's go back to my face so you can see, look me in the eye, or I can look you in the eye. So what we have to do now, what I'd like you to do is go on to show my homework and follow the Seneca task that I've set you today. Okay, it's quite a long one. It's a little bit of revision of nuclear physics, and it's also then looking at quarks and antiparticles. I'd like to just go through the tutorial on that and use that as part of your revision. Remember, next week you have your end of year exam. So I expect you over the weekend to do some revision for that. That's all the AS topics. That's everything you've done this academic year, except for the radial fields work that I did and circular motion work that I did with you. Everything else could come up in that exam. In fact, it probably will, because it's a past first year paper. So what I'd like you to do is make sure you do those papers. You do those 2 papers next week, the multiple choice on Monday, the short answer questions on Tuesday. Okay, oh, sorry, on Wednesday, I apologise. And make sure you've got those done for those days. And then what we'll do is that this time next week, I'll start you off with your first walkthrough of the multiple choice paper, followed by the walkthrough of the short answer paper on the Wednesday of the following week. Okay? Thank you.